All right, last time, let's see. Yeah, okay. All right, so today's lecture. So recap. Last time we covered the basics of PyTorch, how to install them, how to install Jupyter Lab and the Docker and stuff, and then some basics. The autograd demo, if you guys remember, we like manually derived the gradients starting from like Z out to Z to Y to X, and then we went to the module demo. Where you define your neural network as a module, like you inherit from the module class, and then you define your neural network, and then you have a bunch of things that helps you along, such as you can print out the member variables, or the weights or parameters, if you will, and also you could define your negative log likelihood and then call backward, and you can see that it is actually calculating all the gradients with respect to the parameters. And so with the basics covered, today we'll go through the ones that we originally intended to do, which is character RNN. I think this is all right. All right, so any questions from the previous class? Anything that you like, some of you might be confused with or having difficulty understanding? Anything that you guys want me to go over, repeat again in Korean? I mean, PyTorch is, I mean, these libraries are pretty quite confusing when you first try to implement stuff, because they are not really like Python programming. Like Theano, TensorFlow, PyTorch, they're all quite complicated when you first encounter the framework. So if you guys have any question, please interrupt me anytime, any moment. All right, so then if there's a question, we'll go through the character RNN. And so the first character RNN has no minibatch. So we're gonna define an RNN model, the recurrent neural network model, and then we'll define it such that it will only consume one sample at a time. So it's not a mini batch. It's a sample. It's just a like the true stochastic gradient descent, because originally stochastic gradient descent was designed under the assumption that you update per sample, not update per a mini batch of samples. So this is what we're going to do today. And if you guys remember, I told you guys that last time, I told you guys that PyTorch assumes mini batch by default. Like anything, even if you try to implement it in such a way that you only process one sample at a time, it still requires you to have an additional dimension, additional access for the mini batch dimension. So today we're gonna use a little trick and just add one more dimension. So our input would look like this. So it's a line length. When it says line length, it's just the length of the characters. So like length of your name, like Hinton would be 6, and John would be 4, something like that. And the number of letters. So we're gonna use like a one hot vector. If you remember last time, when we're talking about the marriage status, there were 5 marriage statuses. So there was like single, married, divorced, widowed, and like others. So there's 5. So that means there are 5 types of marriage statuses. So we had to prepare 5-dimensional vector to represent each of the marriage status type. It's the same with the alphabet letters, because there were like 57 characters, if I remember correctly. So 57 character means we need to prepare a 57-dimensional vector to represent each alphabet. Like A would be 0, 1, 1, 1, 1. B would be 0. No, I'm sorry. So like lowercase a would be 1, 0, 0, 0, 0 all the way. And B would be 0, 1, 0, 0 all the way. C would be 0, 0, 1, 0, 0 all the way, something like that. So that is why our input would be line length times 1, which is the fake mini-batch dimension that I just talked about. So line length, the length of your name, and the fake dimension that indicates we're going to use only one sample at a time, and the number of characters, 57, if I remember correctly. So the first thing that we need to do is, first of all, I mean, I already showed you guys, we need to load the names, load the list of names from 18 different origins. So like Czech, German, so Czech, German, Arabic, Japanese. We've looked at some Korean names which looked weird. So we first load them all up, and then we're gonna put them into a dictionary. So it's gonna be named category lines. So category lines, like Italian, and you get the first 5 entries, you get abbandonato, Battangelo, whatever. I don't think abate doesn't seem like an Italian name. Anyway, so you have a dictionary of names per origin. So you have that. And by the way, did anybody try out my notebook that I uploaded and try to like load the names and hit trouble? No? Okay, that's fine. By the way, let me just get a cup of water. Okay. So far so good. And then, as I said, these are just characters like abbandonato, Battangelo. These are just like string, and we need to convert them to this format, as I said, the line length times 1 times n letters, in order to feed them into RNN. Well, I mean, we first need to implement RNN first, so that there's something that we can feed to. But before that, just as a pre-processing step, we need to think about a way to convert this and like each of them into this format, basically. So for example, a byte would be like 5 by 1 by 57, something like that. So there are some demos. First of all, like letter to index is like, these are just like basically utility functions. So we won't go into detail, but once you define them, we're just gonna, once you define them. For example, like capital letter J would be like all the way 0, like probably somewhere around here is like a small letter Z, and then capital letter A, B, C, D all the way to like J, and then again, all 0. So we're using 57 characters. So 57 character meaning that alphabet has 26 letters. So 52 plus 5, I guess we are using hyphens like dots or commas or something like that. And then, as I said, Jones would be, or it's the same as a bait. Like Jones would be, there are 5 letters, so 5 by 1 by 57. That's it. And then we're gonna define our RNN, which is not quite on RNN. If you are already familiar with PyTorch, then you would instantly see that this is not actually an RNN. This is something that is very like a very naive of implementation of RNNs. So, I mean, even if it's a naive RNN, we still need to define the size of the hidden layer. So, oh, actually, I should have opened up my previous slide. Right. So if this is RNN, then we need to first define the size of this H layer, how large it's going to be. It could be like 50, 56, or 25, 20. Yeah, I mean, I'm sorry, 32, 64, 128. It's totally up to you. But in this case, in our case, this is a pretty simple example. We're just classifying the string of characters into its origin. So I don't think we'll be needing like 128 or something. Let's see what they did. Oh, they did use 128. Okay, that's pretty large. Anyway, So as I said, this is we're inheriting from the module class. So RNN is an like instantiation of module class. And in the init function, we define all the weights, the parameters. So there are in total, how many? There are just 1 and 2 weight matrices. And then there's something called log softmax, which I'll get into later. And then the forward function is where we actually implement the forward operation. Like when we start from the bottom and go to the top, in this case, RNN, so we start from H1 and then go all the way to like HT, the final time step. So this will be our forward function. And because we are only defining the RNN cell, we're not actually going through the for loop. The for loop will be done outside the RNN. So inside, I'm sorry, yeah. So inside, if you remember the RNN, let me see. I think we have 0.6. Right. Okay. Here. Right. So this here is a single update of the RNN cell, like per time step. And this is, for example, this is the ith time step. So in the ith time step, how you derive the new hidden layer is you go through this operation, which is you linearly transform your input, linearly transform your previous hidden layer, and then you add some bias vector, and then you put it through some nonlinear activation function, typically a 10H function. But in this case, do you see that happening here? So I want you guys to take a moment and see if this is the same thing as this. So obviously the answer is no, because there's not even a nonlinear activation function here. You don't see any 10H or sigmoid value. It's just straight up so there's something called cat, which is you just concatenate something like right next to each other, and then you put it through it. So you get the input would be the X here. Input would be the X, a hidden is H, and then you concatenate them. So if I draw a picture here, you have the X vector, and then you have the previous hidden vector, which is, let's call this HI minus 1, and this is XI. And basically cat operation just puts them together like side by side. So now you're like combined would be a very long vector. Then hidden, so you can see, so the next, the HI here, so we have the HI minus, so the current HI, the new HI, how do we derive that? So we have a I2H, which is just a simple matrix, weight matrix, plus there would be, I mean, if you guys remember the previous lecture, there is like bias true here. Right. Okay. So this is just a simple linear layer. So what's happening is you get, if you combine, if you call these like the combined, then all you are doing is just W combined plus B, and there's not even like a nonlinear activation function. This is it. Your new HI is just simply you concatenate them you put them together, your input and previous layer, and then you put it through a linear operation. Just simply multiply it by a weight matrix plus a bias vector, and that's it. So there's not even like sigmoid function here. So it's a very very simple form of RNN. That's why I call it a naive RNN. And your output, so the way this first example is implemented is that every single time step, so where's my, okay, so every single time step, let me just, there's an output. So there's output, and there's output here. Oh, what's happening? So there's also output here. So this will be your output 1. This will be your output 2, all the way to output T. And all right. So all right. Okay, sorry. All right, so you can see that there's output variable, and it's just another linear combination of your combined the x and y, the x and h, the concatenation. You just linearly transform them again using a different way. Now there was I to H, which is like input to hidden, I to O, which is input to output, and that's it. So it's just exactly the same operation as it. It's just using different set of weights, and that's it. And then your output goes through a softmax, which is not exactly a softmax because it's log softmax, but I'll get to that later. But you can think of this as softmax operation. Softmax operation, I explained last time. So it's for multi-class classification. All right, so you can now see why I drew this O, the output at every time step. And it is kind of weird because how intuitively, character, we would, we would assume that the character level RNN, which is just classifying your name, would have this kind of framework. Let me just do everything right. Yeah. Because all you're doing is you're feeding your names character or letter by letter, one at a time. So this will be like HINTON, and once you've completed the input to your RNN, the name, then that's what when you take the final hidden layer HT, and then put it through a softmax to do like an 18-way classification. 18 because we have 18 origins, like Czech, Arabic, German, like 18 countries. So feeding the names first and taking the last hidden layer and putting it through softmax, that should make sense. But here, that's not what it is. They have the output at every time step. So it's just, again, like it's just lazy implementation. This in this tutorial, the original author just decided to put output at every time step and then use only the last output, because we have like, if we have like Hinton six length name, then we'll have 6 outputs, but all we need to do is take the last output and then use backprop based on that last output. So that's why this guy just decided to implement output variable every time step. It's kind of like lazy coding. That seems to me, it looks like a lazy coding. And all right, so the last one is in hidden. So every time you like feed a new name into your RNN, you need to reset your hidden layer to zero values, because what I'm saying is your H1s should start with 0, like fresh start, and then so there will be H0 here, and it's all zeros. And then once you start putting your names or letters like HINTON, that's when you start updating your hidden layer. So this is when you initialize your hidden layer to a 0 vector. All right, so then we have the RNN. So okay, so we define the size of the hidden layer, and then we instantiate the class, and then we test some stuff. We like try to convert your like capital A into like a function, and then do something like that. So what's happening here is that first you initialize your hidden layer, and then you put your hidden layer. I mean, so if you've noticed, we don't have a hidden layer here, interestingly. So all we have are the weights and the softmax. There is no hidden layer, so we need to provide the hidden layer explicitly along with the input. So that's why the forward function receives input X and hidden layer H. So here we need to define a hidden layer ourselves explicitly and then put that into your RNN. So what's happening is just it's a proof of concept. You convert your capital letter A into a X or the input tensor, and then you put your tensor into your RNN. So because we've instantiated RNN here, so you put your input X, your hidden layer H, and then you put it through your RNN and see what happens. see if it gets updated properly. And the output of your forward function is output, which is your classification, the softmax output, which we don't need until the end of our character, and the next hidden layer. So this is xi, this is hi minus 1, this is hi, basically. Then you print out your output, which should be 18-dimensional vector. But it doesn't mean anything. Like, it's just a bunch of numbers. And I said this is kind of like a softmax. This is a log softmax. So because at the end of our tutorial, we're going to use cross entropy or the negative log likelihood to backprop. So in that case, it's better to use log softmax than a pure softmax. It's just some trick used by like Python users. But you can understand that like the largest number here should be the prediction. I think like, do we have a large, like, I think this is our largest number, which is what? Which is like, interestingly Korean. Is that true? Anyway, you put a single character and see what happens. You put a name. Well, you first create a name, and then you need to turn it into a tensor. So this would be like 1 to 6 by 1 by 57 tensor, and then you put your first character in, which is capital A. So it should be the same result, like the capital A here, capital A here. You're just putting capital A into your RNN, and see what happens, and then that's it. And so this is another utility function. You have your softmax output, and then you want to turn that into an actual country. So okay, so I was right. You put the current output, which has this as the maximum value. This one, it is indeed Korean. All right. So you have everything you need. Like, you have the utility functions that changes your input to a tensor. You have the RNN cell, so you're ready to train your RNN network. But in order to train it, you need a data feeder or sample feeder, where you randomly sample a name from the bunch of training names, and then you need to randomly select it and then feed it into your RNN. So that's what's happening here. It's just called random training example. So as I said, we're training our RNN one name at a time. We're not doing a mini batch. We're doing like a single sample gradient, this stochastic gradient descent. So we're just, when you call this will just simply, when you call this function, it'll simply select a name, and that's it. And yeah, it'll select a name and then turn it into a tensor. So like Albert would be, as I said, 6 by 1 by 57 tensor. So we just call it for 10 times as a proof of concept and see what happens. So it'll just randomly select a name from different origins. Like the origin or the country would be selected randomly, and the name will also be selected randomly. So if you call it 10 times, then it'll be like 2 times Portuguese, like Irish, Portuguese, Russian, and also names would be different, like Ramirez, Fonseca, Kennedy, Gouveia. Gouveia is a weird name. All right, and we set the criterion, the loss criterion, to be a negative log likelihood. So NLL loss. So that's why we use log softmax, not the actual softmax. So okay, so everything's done. We even have the data feeder, and now it's time to actually train our network. So we define a train function, and before that we set the learning rate to 0.005, which is, I guess it's a decent number. I think people usually use 0.001, between 0.001 and 0.001. So like between like 10 to the minus 3, 10 to the minus 4. 0.005 is a bit steep, I guess. But anyway, so the train function would have our category tensor. Category tensor meaning the Y, the label, because our label should be 18-dimensional vector, because we have 18 characters. 18 countries. So category tensor would be 18-dimensional vector. Line tensor is the name of the length of the name times 1 times the character, so which is like 57. So that will be our input to the train function. And then, as I said, we need to initialize the hidden layer to zeros first, and then zero grad is that you want to initialize all your gradients to zeros. As I said, if you define a module, or if you use a module to define your neural network, then it'll automatically start to backtrack your gradient whenever you're like put it through a forward function. And because of that, you need to reset your gradients every single time you want to train your network. So this is that zero grad. And then so depending on the size of your name, so if John, then 4, if Albert, and then 6. So that's what's happening here. So depending on the length of your name, you just feeding each character into your RNN, and then you're updating your hidden layer. So that is why that's what's happening here in the forward loop. And then once you have the last output, so we throw away all the outputs from the intermediate steps, and we just take the last output. After we've gone through the for loop, we just take the output, and then that's what we need to use to do the backprop, the final output, because that's when we see the end of the name, like HINTON, Johnson being JOHNSON. Like we need to see the end of the end of our character of our name, and then use the output from there to do the backpropagation. And the criterion was negative log likelihood loss. So it's negative log likelihood loss, our prediction at the last time step, and the true label Y. And then we do the backward. If you guys remember, like the backward is when you do the backprop. So now, once you've called this, every single parameters will have its own gradient values. So let me just go back. As I said, once you've called the backward, each parameter of your module or of your neural network will have a grad value calculated by PyTorch, the AutoGrad engine. So that's what's happening here. So we just need to call this grad and then use this grad to update each parameter. And typically we use optimizer called like Atom or Eta Delta or RMS prep, but here we're doing it manually actually. So what's happening is that we take each parameter in our RNN neural network, each parameter P, and we have the gradients of that P, and then we simply add that to the original value. So add underscore is so what's happening here, let me just write it down. So for example, there were two parameters, I2H of our RNN, and there was I2O, right? And then each I2H and I2O would have W the matrix and the B, again W the matrix and the B, and here, if you call the parameters, what's happening is that the P will be WB, like iteratively, and add underscore is what's happening here is that, for example, if we take W, let's call this WH, for example. So what's happening is WH is simply, it's an in-place addition. So WH is WH time plus, there's negative learning rate. So there's negative 0.005, negative 0.005, and times the grad data. So this will be the loss function. The gradient of the loss function with respect to the current parameters. So this line here represents this operation, and this is exactly what we want, which is gradient descent. So because there's negative, we can forget about forget about the addition here. So basically, we're just taking a gradient descent step using this operation, and we do that for WH, BH, WO, BO every single time. I mean, every single time per name, not per a mini batch of names, per name. And then so after so I guess this is just a single train. So this here train is a train function for a single name, not a mini batch of names. And then once you've trained it, you get the output, and then you get the loss. So you want to track the like how your loss value increases or decreases over time. Well, I mean, obviously, ideally, you want your loss value to decrease over time because you want the RNN to learn something so that it learns to push the negative log likelihood value like downwards. All right, so we've defined the train function. So now is actually the time to run the train function. How many times? That's up to us. So I guess we're going to update train function 1,000 times, meaning that we're going to randomly sample a single name 1,000 times, and then update RNN with that. And there are just some print functions, like we want to print our loss value every single 50 steps, and like something like that. And we want to have like a graph plot every 10 steps, something like that. So these are just like technical details, but all we're doing here is that we just, because we want to update our RNN 1,000 times. So we call our for loop 1,000 times, and then each time we randomly sample a name, and then we put it through a train function, and then we get the loss output, and that's it. And then the rest is just printing functions. So let's try to run this 1,000 times. Oh, okay. I guess I didn't. What did I not? Random train example is not defined. Really? Okay, so when I guess I should have run every single cell. Okay, run this, define the RNN, define the category of, okay, output is not defined. Okay, so I'll just, all right, define this, define the loss, define the train function, and now we can run it. All right, so you can see it. So I've set it such that every 50 iterations, for every 50 updates, I want to output I want to print out the current output. And you can see it is not doing so well. So in the first 50 iterations, our RNN neural network decided that Loong is a Russian name, which is not true. Like it's all X's. There's not even a single like correct. Okay, so Duong Vietnamese. So okay, so it learned that at least this is at least like correctly calculated that Duong is Vietnamese name, and the other all X's. So if you plot this, if you plot 1,000 updates, and it looks like this. So yeah, it's I guess it's going downwards. So there is like a downward trend. Like you can, yeah, you can draw a line. Like I guess if you wanted to do a regression, it would look like this. But I've only trained it for like 1,000 times, so it's probably not enough. And then, okay, so this is just a fancy thing that the original author did, trying to show you guys, trying to basically visually represent how well it is doing per countries. So this is a confusion matrix. If we plot this, well, it is not doing so well. So like this, I think one of this and one of this is predicted, one of this is the actual, but it doesn't really matter because it's no, it actually does matter. I forgot which one was which, but anyway, the brighter the diagonal line is, the better the model is doing, because like given a Czech name, it is actually getting the Czech name right, and given a German name, it is actually predicting it to a German category, something like that. So, for example, here, at least it's doing a fine job with respect to the Greek names. So Greek here and Greek here. So the accuracy is about 0.8-ish. It's like almost 0.9. So, and Polish name is also doing pretty good job, like Polish and Polish. But all the other names, not so well. Okay, I guess this is the true and this is the predicted, because for all like Czech, German, Arabic, Japanese, it's all predicting Polish, because the RNN hasn't learned much yet. So that is why it's just yeah, constantly predicting Polish all the time. Was that true in our case? I actually don't see a lot of Polish in our prediction, but anyway. Right, so let's just run it a little further. Let's go 10,000 times, see what happens. Still a lot of X's, a lot of X's. Well, you start to see some correct predictions, but still not doing so great. Ah, man, a lot of X's here. Okay, you see a lot of correct predictions. The checks, a lot of checks. All right, let's see our loss plot. Okay, clearly, okay, so clearly there is a downward trend. So we started from like 2.9-ish or something, and then I mean, there's a lot of variation, like, but still, I guess we're somewhere around here, which is like 2.1, 2.2 or ish. And then if you draw your confusion matrix, okay, so clearly it's better than before. Like last time it was all here, right? So it was all Polish, but now you see some bright lines along the diagonal section, like here. And okay, so this is also interesting. So for Korean names, the RNN is confusing with Chinese names, but I guess that's understandable because if you remember, there were only like 100 Korean names. So there were like very small number of Korean name samples to actually understand what Korean name patterns are. So it's understandably, it can be confusing with Chinese when Chinese names are presented. All right, so far, any question? We're gonna try to convert this to a mini batch version with actual RNN. So because this was a fake RNN, like a naive RNN, so before we actually do that, or I'm not gonna do that, I've already wrote that code beforehand, but I'm just gonna go through a line by line again. Any questions so far? Nope. All right. Well, we go to mini batch char RNN. So some functions we're just gonna recycle because like things like name to tensor, letter to index, these are recyclable. I mean, obviously, loading up the names is also, I'm just gonna recycle. So you do this and then you get the same output. You just load a bunch of names and then put that into a dictionary. So now, if you remember, there were before it was a letter to. So these two are exactly the same. Letter to tensor, which means that you want your like capital A become like 0000100. Your like lowercase b being like 0100000 or something like that. So this is the same. But the other thing there will be some changes along the way because we want to change the previous example, which is to update your RNN per sample, but we're going to change it so that we're going to update our RNN per a mini batch of samples. So we don't want to change or convert a single name to a tensor, which was a length by 1 by number of characters. But instead what we're going to do is we're going to take a bunch of names, like 10 names or 20 names, like a mini batch of names. We're going to take a mini batch of names and then convert that to a tensor. So it's going to be length, name length times a mini batch size times number of characters and letters. So from now on, we take like a bunch of names and we turn that into a bunch of tensors. But one thing to remember is that when you have, so we need to think about something called a padding. because each name has a different length. For example, let's say that we're packing Albert and John together. So this is just a simple mini batch of 2 names. That's it. So just 2 names in our mini batch, and we want to convert these 2 names into a single tensor. And okay, so there's a question. RNF forward. 바탕화라는 코드는 컨캣을 먼저 okay, so just to answer in Korean first and then I'll repeat that in English. 그 아까 방금 전에 보여드린 거는 실제 RNN이 아니에요. 그러니까 왜냐면은 실제 RNN은 그 요 식을 취해야 되는데 이 식을 취해야 되는데 방금 전에 RNN은 네, 방금 전에 RNN 보시면은 W랑 X를 그냥 붙여버려, 더한 게 아니라 붙여버려요. 그냥 이렇게 긴 벡터로. 이제 2 개를 더한 게 아니라 아까 그림 그려드린 대로 이제 제가 한 번만 더 그려드리면은 그러니까 더한 건 이렇게 2 개 더해가지고 같은 디멘션에 그게 나온 거고 이게 W고 이게 H고 이게 X면은 이게 이제 H 플러스 X고 이게 H 플러스 X고 컨캣은 자리가 모자라네. 컨캣은 이렇게 된 게 컨캣이에요. H랑 X를 이렇게 붙여버려가지고 이제 각기 살아있는 거고 그냥 대신에 이제 사이즈가 커진 거예요. 그래서 이거를 여기서는 이제 두 개, 잠깐만요. 이렇게 생긴 거를 여기서 이렇게 하나는 I2, O로 보내고 하나는 I2H로 보내고 그렇게 해서 다음번에 HI 이거는 OI 아웃풋 이렇게 되는 거예요 지금. 그러니까 제가 보여드린 요거랑 전혀 맞지가 않아요. 지금 보시면 그러니까 지금 이거랑 전혀 맞지 않아요. 이렇게 이대로 하려면은 그러니까 X에다 따로 트랜스포메이션하고 Y에다 따로 트랜스포메이션하고 그 다음에 이제 그거를 넌리니어 펑션을 이렇게 뭐 탄H나 이런 거에 보내야 되는데 이건 지금 그냥 단순히 2개 합친 다음에 이렇게 매트릭스 오퍼레이션 한 거래 가지고 굉장히 실제 RNN이 아니라 굉장히 뭔가 다른 아주 멍청한 RNN이라고 볼 수 있죠. 네. So what she asked is that whether we whether we actually, in order to follow this previous RNN, the naive RNN, whether we should like add these 2 or concat these 2 is just so it was basic question coming from like slight confusion. So to repeat myself again, here what's happening here inside the forward function is you concatenate H and X to make a horizontally longer vector and then do a linear operation so that we get HI and OI out of it. So we're not adding these 2 actually, right? All right, so going back to here. All right, so I was talking about the padding. So okay, so before when we were converting a single name into a tensor of length times 1 times letter, there was no problem. We just convert each alphabet into like a 57 dimensional vector, and then we just concatenate everything. But here we have 2 names which have different lengths. So this should be a 6 by 1 by 57, and this should be a 4 by 1 by 57. But the PyTorch, or not just PyTorch, like any of these like deep learning frameworks like Theano, TensorFlow, probably MXNet, like all these PyTorch and stuff, they require you to have a fixed size tensor to So yeah, you need to operate on a fixed size tensor. Your tensor cannot have like a jagged line. Like if you draw this, for example. So for example, if you forget about the one dimension here, then it'll look like a 6 by 57. So 6 by 57. Yeah, okay. I'll just forget about all like 1 and 57. Just for example, let's say your name should have like one is Albert, which is like 6 characters, and the other is John, which is 4 characters, and like this is a void. Like there's nothing there, and then you can think of generalizing them to a tensor like this. So it'll be like a matrix, and it'll be like a let's just say this is like a 57 dimensional. There's 57 here, and this will be 6. This will be 4, and then so this matrix represents Albert. This matrix represents John, and then you want to make them into like a mini batch. So you like put them together, and then now the lines are not aligning because they have different lengths. And I mean, for memory efficiency, you would like to put this into your RNN. You just have like 6 by 57 matrix, 4 by 57 matrix, like put them together like a sandwich, and then you put them into RNN, and you hope that it will work, but it actually doesn't work because, as I said, all these deep learning libraries, they don't support these jagged lines. These like uneven matrix tensor is not supported in these deep learning libraries. I mean, these days there's something called like sparse tensors and jagged, like legged tensors stuff, but those are like pretty advanced stuff that you don't need to care about right now. So the classic way to deal with this uneven tensor is to just put a bunch of zeros here. So you put 0 zeros, and now you have the same length 6. Like these literally all 0 0 0 0 0. So now it becomes like 6. So it's kind of like a waste of space because you're simply padding the shorter one with bunch of zeros to just to make the ends meet, just to make the dimensionality like consistent. And this is called padding. And that's why you don't want to have like a very long name and a very short names. And then if you sample in a way such that your mini batch consists of like really long name and a really short name, then that means that you're gonna have a lot of zeros taking up your space and taking up your memory. And your memory is very precious resource because you typically train this neural network in your GPU, and GPU has like only so much memory available. Like the maximum is like probably 18 gigabytes or something. And you don't want to waste a lot of memory just because just to make the ends meet, just to put a lot of zeros. But so there's our different like strategies to cope with that kind of waste of memory situation. But we're not gonna we're not gonna address that today. But today we just suffice to know that there's this padding is necessary to actually make our neural network work. So this part. And this is exactly what's happening here. So first of all, it is no longer a single name, but we're receiving a list of names. So like Albert and John, like in a list or something. And then in order to properly pad your tensor, you need to know the maximum length of the longest name in your mini batch, because that's going to be the standard. That's going to be the criteria, and all the others will be like shorter than that. So all you need to do is just put a lot of zeros. So you get the maximum length calculated. So you take the maximum length, and then you prepare a big zero tensor, which is next length, the length of the names, like how many names you have, or the size of your mini batch, and 57. So in our case, this will be like 6 to 57 basically. And then you enumerate your name per name, like you go through Albert and John, and then you just fill in the zeros, because your tensor now is just a big zero tensor, and you just need to fill in those, like the big space with ones basically. So like, as I said, like capital, I mean, small, lowercase a being like 0, 1, 1, I mean, 1, 0, 0, 0, 0. So you just, per character, so per name, per letter, you just need to find the right place for the letter and just tick that in, turn that into a 1. That's it. And then, so if you run this now, if you run this, so what I'm trying to do here is I'm giving it 3 names, Jones, Ham, and Johnson. And let's see what happens. Oh, okay, I need to delete these. What's happening here? Oh, I didn't properly load my stuff. I loaded this. Weird, I didn't know. That's weird. Okay. All right, so you can see if letter name, the length of name is 5, 3, and 7. So when you put this into, when you turn this into tensor, it should be 7 by 3 by 57, obviously. All right. So okay, so now we have this function. We just need to, from now on, we just need to sample a bunch of names per update, and then turn that into a tensor like this. I mean, like this, and then feed that into your RNN, and that's it. Again, so now implementing the correct way to implement a vanilla RNN. We're not going to implement GRE or LSTM. I mean, if you're interested, you could try that. But here, we're just going to try to replicate the original RNN, which is this, right? So for okay, so it's same inheritance from the module class, but we define the input size and the hidden size just for, so input size meaning the size of the batch, basically. We're gonna train, we're gonna update our RNN in a mini batch fashion. So it's easier if we fix the size of the mini batch before we implement the RNN. So that's what's happening here. So this is the size of the mini batch. This is the size of the hidden layer, and right. So hidden size was hidden size. Now, I'm just sticking to the original vanilla RNN. So I'm going to call this W a WH. I'm going to call this U a WH. I mean, so this is going to be WX because it's attached to X. This is going to be WH because it's going to be operated on H. So I have WX and WH, and then simply it's just a linear operation, and the WX should be input size by hidden size because we're turning our input into a hidden layer, and then this is going to be the same square matrix. Hidden layer, hidden layer. And notice that I've set the bias to false because I want to replicate this exactly. I don't want WX plus B, WH plus B. I want 1B here. So this is, I turn the bias off, and then I'm preparing a separate B because I've turned the bias off. I need to have a separate bias vector. So I'm gonna call that a B, self B, and it's just a simple set of parameters which has the size of hidden layer. I mean hidden size, right? And the forward is extremely simple. We have X times input, I mean WX times input, WH times hidden plus B, put it through a nonlinear activation function. In this case, 10H. That will be our new hidden layer, and so we just return the hidden layer, right? So far so good, right? Same utility function, we need to like reinitialize our hidden layer to zeros. And compared to before, it should be a batch size of hidden layer because we're using a mini batch of samples. So if you remember previously, init hidden was 1 by hidden size because we're taking one name at a time. So we're updating one name, processing one name at a time. So the hidden layer, we need to have the hidden layer for one name only, but in this case, we need to have a bunch of hidden layers per name. So that's why when you init your hidden layer, it is batch size times hidden size, right? Okay, and to make it more clearly, to make it more like kind of like elegant, or to be more separated, to make it more separated. Before, RNN had the output function inside, which is kind of weird because the RNN should be all about RNN. The output should be a separate function. You don't want your RNN to take care of the prediction part automatically inside, which is kind of like a bad modularization. So here I'm having a separate class called predict. So RNN will only be responsible for updating the hidden layer only, and using those hidden layers, I'm gonna use another function called another class called predict, where it gets the input and it spits out where you feed in the input, which would be the hidden layer, and then spits out a softmax. So this is you can see what I'm trying to do here, right? So you initialize the predict function, predict class with a simple linear operation. This corresponds to I2O in the previous char RNN example. So we have a linear operation, linear operator, and then we have the softmax, which is the same as log softmax before. And so when you do a forward, you have the input, which is the hidden layer of the RNN. You put it through a linear operation, and then you put it through a softmax, and then you have your 18-way classification. So is it clear that why I separated the RNN part and the predict part? I just wanted to give them a separate role assignment. And same as before, we set the hidden layer to 128, and then we instantiate the RNN. We instantiate the predict function as well. So RNN pred, and okay. Right, okay, so I think this is, okay, kind of, all right, we don't need to talk about it. This is the same, you have the output, and then you're trying to predict, you're trying to map that to an actual country name. Another difference is that before the random training sample, the function, all we need to do was have a single sample randomly chosen from a bunch of names, but now we need to choose a mini batch of samples from a bunch of names, and we want to do it smartly. We don't want to select a single country and then select a bunch of names. Like, we don't want our mini batch to consist of only Portuguese names or only Japanese names. We want our mini batch to consist of like names from different origins, like Korean name, Japanese name, English name, German names, and all kinds of different origins. So that's what's happening here. I'm trying to randomly choose a set of different countries, and then per country, I'm sampling a random name per country, and then I'm forming a mini batch tensor. So you can. So this is the conversion function that I defined like above. So you get a bunch of names from different origins, and then you put that through a name to tensor function, and then that's how you get the names tensor, and also labeled tensor, which would be like a mini batch times 18, because 18 being the number of countries. All right, so let's try to run this for example. Run this. Okay, sorry. Okay, I don't need an example, so I just need to run this and then run this. What? What's not defined here? Random training examples. Sorry about that. Ah, man, what's happening here? 1911. Oh, wait. Okay, some typos. Country name. Right, okay, so what's happening here is that I'm trying to sample 5 random names for my mini batch, and they are from Arabic, Vietnamese, Irish, Czech, German origin. So I'm just doing it randomly. And then the corresponding names are Aryan, Hun, Queen, Patrick, Skokin, and Blumenthal. Blumenthal. That doesn't sound like a German name. Anyway, so this is my a set of a mini batch of like the origin or the label and the names, and the tensor is what? So the label tensor has, yeah, right. So Arabic probably is like name 2. Like remember the Korean was 16, Arabic is 2, Vietnamese 5, Irish 8, Czech 0, German 1. And okay, so now you got to check that if our mini-batch tensor is converted correctly, and you can see that 10 is the size of the maximum length, like the longest name in our mini-batch, which should be Blumenthal, and Blumenthal indeed has 10 characters, so it's 10 by 5 names by 57 characters. So you can see that is working correctly. So we're good to go. So yeah, we define our loss to be the NLL loss. Ah, man, okay. Port. Right. And let's see. So this time, so this is the same train function. I'm going to use the same learning rate. And compared to before, when before there was only one neural network, which was RNN, that took care of updating the hidden layer and also producing the output. But now we've separated those roles. We have the RNN part and the pred part. So we need to like separately reset the gradients, and then per single update we have a mini batch of names, and we don't need to care about whether we have a single name or a mini batch of names, because as I said, PyTorch already expects you to feed a mini batch of names. So you don't need to care about like change anything. You just need to have the same name tensor and just name like character by character, like letter by letter. You just feed a bunch of letters into your RNN. For example, in our case, we had 5 mini batch of 5 names, so this will be of 5 letters per time step. And so you feed 5 letters per time step until the maximum length, and then you're done. And then you have the final output. You have the final hidden layer, and then put that through your prediction function, and then you get the final output. And then you have the negative likelihood loss, and then you call the backward. And compared to before, compared to before, where we needed to update the parameters from the RNN only, here parameters from the RNN only, we also need to update the parameters from the pred function, the prediction layer as well. So that's why we have 2 loops to update our parameters. All right, and then that's it. So you have the train function, and the rest is exactly the same. Now we can start with like 1,000 iterations and print every 50 steps, plot every 10 steps, and batch size 20. So all right, so we're gonna try to update our RNN with 20 names per update. Okay, let's start the call. Not defined. Did I not define? Oh, I've never defined this. That's weird. Yeah, that is weird. Okay. Right. Okay. I'm just gonna redefine everything. This. Okay, now we can run. You can see it's kind of slower compared to before, because now we're processing 20 names per time, 20 names per update. But if you think about the overall, the total number of names being processed in the entire loop, this should be way faster than processing 1 name at a time. All right, so let's plot our line. Let's see how it goes. Okay, so it's kind of worse than before, I guess. Yeah, the line is only ever so slightly decreasing, and I guess we can run it a bit more, like every 100 time steps, maybe every 50 time steps. Actually, no. Let's just keep it like the same way. Now 10,000 will be a bit a bit too much. So the problem here is that I'm running everything on my CPU, which is not even like a powerful CPU. I'm running this on my laptop, so that's why it's so slow. But if you run this on a GPU like Titan or like GTX 1020 or 1080 or 2080 or even like the state-of-the-art GPUs like V100, this will be way faster, like at least 10 times faster, something like that. Yeah, I don't see a lot of progress here. Now, while this is running, can anybody tell me if there's something wrong with this current implementation of the RNN and how I update it? Before that, does anybody have problem understanding what we've gone through? Like implementing the actual RNN and creating a mini batch of samples and padding them, and I'm padding the different different length names, and then putting it through the RNN, updating it. Does anybody have problem understanding this? No. Okay, then does anybody have any idea why this is kind of like incorrect way to update your RNN? Yeah, there's a chat. Optimizer step. We don't have a step actually. I mean, the correct way to actually update this neural network is to use an predefined optimizer like Atom or RMS prop. We're just, I mean, this is not the biggest problem. I mean, optimizer step. I mean, manually updating it is kind of a problem, but this is not the biggest problem. It should work. There's something to do with output and the time steps. Like each name has different length. So this could be like a big hint. Like each name has different length, and the way we use output and update the RNN, something does match there. No. Let's see. Oh, we are getting some checks here. All right, let's plot it. Whoa, okay, so after 5,000 steps, almost at like 4,900, 4,800 steps, it's rapidly decreasing. So if we had run it like 5,000 times more, it would go like way below and probably learn it properly. Oh, I didn't run the confusion matrix, because confusion matrix probably was written under the assumption that your RNN will produce a single prediction, because it was supposed to receive one name at a time. I didn't take the time to actually change this segment to be compatible to a Minibatch version. Anyway, all right. So if there are no guests, no takers, then the problem with the current implementation is that we are running the for loops until the end of the maximum length name, and then taking the output all at the same time. When some names have shorter length, some names have like longer length, some names have shorter length, but we're taking the output from the same like last time step and then using that as a prediction, which is probably not a good idea, right? So we only have 10 minutes left, so I guess we don't have time to go into the interpretability topic today. Let me just wrap up with this problem here. Let me get my Let me get my iPad ready. Parameter that not related to sample is updated. Parameter not related applied to padding. Pretty close, but all the parameters are relevant parameters. I guess that's as close as you can get. How do I, okay, let me present my whiteboard here. Yes. Okay, so let's go back to our original sample. Johnson and what was the other one? Oh, it was Albert and Johnson. Okay, John. Oh, we can go with Johnson and John. So let's, for example, we're doing 2 sample at a time. So it's a mini batch of two names, and there will be 0, 0 here because of John. This John. So four letters and SON, and this will be padding, padding, padding. So it'll be John, Johnson, and John XXX, which is the padding part, and then you put your RNN, like your RNN will process each letter at a pair of letters at a time. So it gets JJ at first. So J, this is at time step 1, it takes J and J. At time step 2, it takes O and O, and all the way to T4, which is N and N. And T5, it'll be S and padding. T6, O and padding. T7, N and padding. And this is where we, so this is the loop of for I in like the tensor. And this is when we get the outputs. So we have outputs of 2 because we have two names. So there will be output 1, output of Johnson, and there will be output of John XXX. And XXX is not actually an XXX because if you remember, we're padding it with zeros, and and zeros are not exactly nothing. It is something. It is, if you put 0 into your RNN, so this is your RNN, and like if this was your, like previously it was John, so N was put into your hidden layer. So let me hidden H4, and then you have H5, which is 0. You have H6, which is 0, which gets input 0. H7, which gets input 0. And then if you remember the update function, the update formula for the hidden layer, H5 would be sigmoid, or not sigmoid, I'm sorry. This is 10H. 10H, WX plus UHI minus 1, no, this is not correct. WX5, UH4 plus B. Yeah, that's correct. So UH4, now H4 is correct because H4 is what represents the name John. So what we should have done is put the output from here and take John. So this is the wrong output to get. This is the right output to get. But for Johnson, this is the right output to get. So it's a bit tricky. But what happens is when you proceed with XXX after the correct number of letters after John, is that you have 0 here, 0 here. So this kind of goes to 0. So it doesn't really matter. But this part is operated. This part functions. So you multiply your correct representation of John by U plus B, and then put it through tanh, and that becomes your H5. And then you do this again, the same step, which will be H5 and H6, and then that becomes your name, and then you do that again, and that's, so you're kind of like manipulating your correct representation of John, which was already correct enough, but you're manipulating again like 3 times more to get the final representation of John XXX, and then you're using that to get your prediction. And that is why it's a wrong prediction. So so when you backprop with this, when you backprop with the outputs, both outputs at the same time, this will be a correct backprop, but this one will be an incorrect backprop, and it'll just mess up with your U function, because the U function will not really know what to do, because I mean the U matrix will really not know really what to do, what's the correct way to process the hidden layer, because sometimes it says that you've done a correct job, but sometimes it's gone through 3 X's and did something wrong to the representation, and it doesn't really know what to do. So it's kind of like, so that's what's happening here. And if I go back, that's probably why it's having a really hard time trying to adjust, like trying to find the correct way to update the hidden, update the matrix for the hidden layer, the U matrix, or in our case, in this case, WH matrix. So the correct way to actually do pick the right H from a bunch of names with different length is to remember the name, the length of the names actually, and then as soon as you hit the end, hit the like the final character of each name, you kind of like remember the hidden layer at that time step, and then pick it up. So it's kind of like a technical detail, but it is actually very, very important to do that correctly. And the modern deep learning frameworks like TensorFlow and PyTorch, they already have the RNN function, and they already support this kind of like unevenly, like unbalancedly uneven size of names or uneven size inputs, because the sequence that the RNN you give to the RNN often it does not consist of the same size or same length. So modern RNN functions, they have like an option to receive the individual length of the inputs, and then accordingly it'll just produce the correct hidden layers. But in our case, we implemented the RNN ourselves, so that's why we don't have that function. We don't have the functionality. And yeah, so in actually here somewhere there should be like a length argument where you try to retain the hidden layer after you've hit the final length, like the final destination of each length. I mean each name or each input. All right, so did that answer my own? I guess I answered my own question, but does that make sense to everybody? Does anybody have any question regarding what happens if you process through the paddings, the zeros? Why you shouldn't do that? No? Okay, no question. All right then, so I guess this wraps up our journey through PyTorch and the basic implementation of RNN. Yeah, okay, so it's starting this Thursday, we won't go into like this kind of like technical detail anymore. So we'll jump right into the interpretability and like some more interesting, challenging topics in healthcare and machine learning. So I hope everybody is very like crystal clear on what happened throughout this two classes of PyTorch examples, because this will be necessary when you do homework assignment number 3 and the project. So please go through them. And I've uploaded actually there were some errors that I mean, as you've seen, there were some typos and like grammatical errors in this Python notebook. So I'll re-upload this thing again to Classroom so that you guys can have better time with it. All right, okay, so thank you everybody. I'll see you this Thursday, and have a good rest of the day. Bye-bye.